Today, we will start talking about trigonometry, which is going to be precisely the rest of the semester for us. We will start the study of trigonometry with section 7.1 from our book, and we will today listen to the lecture for the angular measures. The section of angular measures is going to help us learn the definition of an angle, the measurement of an angle, and we will talk about two primary measurements, the degree measure of an angle and the radian measure of an angle. Then we will talk about the interconversion between a degree measure and the radian measure. And finally, we will see some application problems where we're going to use these circular measurements of an angle with the arc length of a circular section, and also we will try to understand the relationship between the circular measurement and a circular section from a circle's area. So to define angles, we will start by defining a ray. A ray consists of one point on a line and all points extended in one direction. So in figure 1, E is called the end point of the ray EF, and in the direction of F, I will include every other point. So essentially, it is a straight line that has an end on one side, and the other side is extended to infinity. An angle is the union of two rays having a common endpoint. The endpoint is called the vertex of the angle, and the two rays are the sides of the angle. So if you look in the figure 2, I have the angle DEF. So the sides ED and EF are the sides of the angles. The point E is the vertex of the angle, and we denote this angle by writing angle DEF, or writing this sign which is called Langle, and then writing the three letters associating this measurement. We generally use Greek letters to introduce most of our angles and represent them. For example, the sign theta, which we will read as theta, or the sign phi or phi, or the sign alpha, or the sign beta, or the sign gamma are our common Greek letters that we use to represent an angle. Angle creation is a dynamic process. So we start with two rays lying on top of one another. We leave one fixed place and the other rotate. The one that is fixed out of these two rays is called the initial side. The one that is rotating to give you the angular measure is called the terminal side. In order to identify the different sides, we indicate the rotation with a small arc and an arrow close to the vertex, as in figure 4. As we discussed at the beginning of this section, there are many applications for angles, but in order to use them correctly, we must be able to measure them. Measure of an angle can be done primarily in two ways. One is called the degree measure, and the other is called the radian measure. The most familiar unit of an angle measure is the degree measure, where 1 degree is 1/360th of a circular rotation. What does that mean? If you think of a circle, so on my regular XY Cartesian coordinate plane, I draw a circle, and if I call this one a whole circular rotation, then 1/360th. So that will be a very small quantity. So 1/360th of this entire circular rotation is attributed as 1 degree. So I say 1 degree is 1/360th of a full or an entire circular rotation. So in other words, if I complete the entire circle, if I complete the entire rotation once, then the amount of angle I have obtained is 360 degree. So from the same idea, now we get to say 360 degree is the measure for a complete rotation. And this is, remember, only one complete rotation for a complete circular rotation. So as a matter of fact, we will learn if we do two complete circular rotation, then the degree measure of that is going to be given by 720 degree. So the domain of the circular measurement or the angular measurement is negative infinity to infinity. It can be positive angle, it can be negative angle, and it can be any real number value that we can associate with the angular measurements. There are a few very special angles. Those special angles are called the quadrant angles. So in order to learn that, we are going to start with standard position of an angle. If we draw an angle in such a way that the positive direction of the x-axis is associated with the initial side of an angle, then the angle having the vertex at the origin of the rectangular Cartesian coordinate system is called an angle in standard position. For example, if we look at figure 5, see how the initial side is coincident with the x-axis. The vertex of the angle is the origin of the Cartesian coordinate system. Hence, the angle that we are seeing in blue is an angle in the standard position. In our class, we will precisely be interested in angles which are in their standard positions. An angle is going to be called a positive angle if the terminal side is obtained by a rotation in the opposite direction of the clock or in the counterclockwise direction. Whereas an angle is going to be called a negative angle if the circular rotation of the terminal side has happened along the rotation of a clock. So clockwise rotation generates negative angles and counterclockwise rotations generate positive angles. For a situation as we have described for an angle in the standard position, we designate 5 special angles as quadrant angles. These are the angles 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Why we call them the quadrant angles? To understand that, we are going to first define what are the quadrants. So again, think about our regular Cartesian coordinate system. As it appears, it has divided the entire plane of our discourse into 4 regions. The right top region is called quadrant 1 and denoted by uppercase Roman letter I. The top left region is called quadrant 2 and is denoted by uppercase Roman letter II. whereas the bottom left region is called quadrant 3, and we use 3 uppercase Roman I's for quadrant 3. And finally, the remaining region is the fourth quadrant, and we represent it by the Roman letters I, V. The angles that has the initial side on the x-axis, positive direction, and the terminal side is also coincident with the initial side. So both initial and terminal sides are on the positive direction of the x-axis, is the angular measure of 0 degree. And this is our first quadrant angle. An angle that has the initial side in the standard position or coincident with the positive direction of the x-axis, and the terminal side is coincident with the positive direction of the y-axis, is 1/4 of the entire circular rotation, and it is denoted by the circular measure or the angular measure of 90 degrees and called right angle. This is our second quadrant angle. An angle in the standard position or having the initial side coincident with the positive direction of the x-axis and the terminal side coincident with the negative direction of the x-axis is called a straight angle, and the measure of this angle is 180 degrees. This is our third quadrant angle. As I said, this is called the straight angle because it gives rise to a straight line. For the fourth quadrant angle, we are going to think of an angle in the standard position that has the initial side coincident with the positive direction of the x-axis and the terminal side coincident with the negative direction of the x-axis. Negative direction of the y-axis. So this will be the situation, and the angle is a positive angle, so we are going to go counterclockwise. That angle is called 270 degrees and is our fourth quadrant angle. The fifth quadrant angle is a complete rotation of a circle. So we start with the initial side coincident with the positive direction of the x-axis. We do a complete rotation along the circle and we get the measurement of 360 degrees, which is our fifth and final quadrant angles. After being a little bit familiar with the angular measure degree, we are going to introduce the angular measurement called radians. In order to understand that, we're going to understand a very special relationship between the arc length of a circle, the radius of a circle, and the circular measure of an angle. An arc length, generally denoted by small s or lowercase s, is the length of the curve along the arc. Just as the full circumference of the circle always has a constant ratio to the radius, the arc length produced by any given angle also has a constant relation to the radius, regardless of the length of the radius. This ratio is called the radian measure of an angle. So to understand what we have just described, we're going to start working on the relationship of the radian measure of an angle, the radius of a circle, and the arc length. To do so, I'm going to remind you about one of our favorite formulas about a circle. Remember, the perimeter of a circle is something that can be described by a well-known formula. So I say a perimeter of a circle of radius r units is always given by a beautiful formula, which is 2 times pi times r. Also recall, pi is a spatial number which is going to have the value approximately equal to 22 over 7. But it is not exactly equal to 22 over 7. As we know, 22 over 7 is a rational number. So I'm going to say that. Note that 22 over 7 is a rational number. And pi is irrational. These values are pretty close to each other. Doesn't mean that they are exactly equal to each other. So I say, so pi cannot be exactly equal to 22 over 7 because one is rational, the other is irrational. You can also think of pi as a number which lies between 3 and 4. This is a very special number for us in a trigonometry class. So if we go back to the perimeter formula and try to understand what it means, think about a complete rotation of a circle. If someone asks you, you started at a point, say P, on the circle, you completed one complete rotation, knowing that the radius of the circle is r units. Say you are at the point P, you decided to walk along the circular line and complete one full circular rotation. How much distance you have walked. So the length of the outer periphery of the circle is the perimeter of a circle. And the perimeter of the circle is given by the formula 2 pi r. So we will start with this formula and we are going to manipulate this formula to generate the formula for arc length for any specific given angle. So what we do? First, we are going to understand that a complete circular rotation stands for 360 degrees. 360 degrees, a complete circular rotation, stands for the angle 2 pi in the radians. So there is a very nice relationship between 360 degree and 2 pi, at least I can see that now, because one can now say, well then if I divide both sides by 2, I get 360 degrees divided by 2 equal to pi. Or in other words, I get to say pi is equal to 180 degree. So that's a very nice relationship between the radian measure of an angle and the degree measure of an angle, which we will generate very soon. But at this point, let's go back to the perimeter formula one more time with a little different situation. So think about, again, a complete circular rotation. Think about the angle that has the initial side along this radius, say r, and think about a slice of the circle. Say the angle here that it has made is a measure of theta. Say the distance from this point, from the initial side of the angle to the terminal side of the angle, the circular distance is s units, which we call the arc length. I want to find out an expression for this arc length. So what we say 2 pi r is the arc length if the angle is 2 pi. Remember, 2 pi r is the arc length. That means this S is all of the circle. If the total angle is 2 pi, the full rotation, so how much will be the arc length if the total angle is only 1 unit? So that's a simple calculation. 2 pi being the angle, the arc length is 2 pi r. So if I want to know how much is the arc length if the angle is 1, well, how do I change it to 1? Well, the total arc length was 2 pi r. Now I divide 2 pi r by 2 pi. So if the angle is 1, then the arc length is r. But remember what I'm interested in. I am interested in finding how much is the arc length if the angle is theta. So let's change it that way. So if the angle is theta, then the arc length is going to be r times theta. And this is our simple formula. So we will say this arc length S is r theta. So I have explained you how to interpret this formula. It is not expected from you that you should also be able to interpret this formula, but what I want you to remember is this formula for finding the arc length. So we'll go back where we described this formula. We said that S is equal to r theta and theta is equal to S over r are the conversion formula for a circle of radius r, giving us the arc length S by an circular cross section of circular measure of theta. The very important fact that we're going to remember now that this computation formula only works, so make a note here, this formula only works if the angle is measured in radian. If you remember how I found this formula, you would know that I was using 2 pi corresponding to 2 pi r arc length. So it only works for radian measure. And we will talk about problems very soon. So now we will extend it a little further. We're going to determine a relationship between the degree measure and the radian measure of the same angle. So we have already built up a lot of work, and that is going to help us understand this interchangeable relationship. Remember what we said. We said 180 degrees stands for pi radians. That we have done already because 360 degrees stands for 2 pi radians. So 180 degrees stands for pi radians. Okay. So 1 degree will stand for pi over 180 degrees. In fact, should say 180. And then theta degree should stand for pi times theta over 180. So what is my conversion formula? If I am trying to change a degree measure to a radian measure, then the process is multiply the degree measure by the factor of pi over 180. The same formula is going to now help us find the interrelationship or the conversion formula from a radian measure to a degree measure. So let's get back to what we had already. We had pi radian measure stands for 180 degree. So 1 radian measure stands for 180 degree over pi. So theta radian measure stands for 180 degree over pi times theta. And that is our conversion formula. So now we say if someone is wanting to change a radian measure to a degree measure, then the process is to multiply the radian measure by a factor of 180 degree over pi. So one thing I want you to notice right now is if you look at all these discussion so far, for every single time we're talking about the degree measure, I am either using the word degree or I'm putting that little circle in the power position of the measurement. But for radian measure, I'm not using any unit. So radian measure, we are going to pretend that that's unitless quantity, even though we understand that there is a unit and the unit is radian. Okay, so let's carry on. Our next topic is coterminal angles and reference angles, and this is also of immense importance for the rest of our trigonometry learning. Coterminal angles are two angles in the standard position that have the same terminal side. And a reference angle of an angle is the size of the smallest acute angle, and we generally denote it by T prime, formed by the terminal side of the angle T and the horizontal axis, which I generally say it's the angle between the terminal side of the given angle in the standard position and the nearest direction of the x-axis. So let's understand the two concepts of coterminals and reference angles. So see, in the pictures, I have an angle in the first quadrant. So the terminal side is in the blue, and the angle between this terminal side and the nearest direction of x-axis is the positive direction of the x-axis. So the reference angle of the angle T is itself. Whereas if the terminal side is in the second quadrant and I wanted to know what will be the reference angle, so your original angle is the angle with the initial side being coincident on the x-axis and the terminal side in the second quadrant. To find the reference angle, what we do, we find the angle between the terminal side and the nearest direction of the x-axis. That's the reference angle. Similarly, if the angle is the third quadrant, then your original angle is in the standard position, terminal side in third quadrant. So the reference angle is the angle between the terminal side and the nearest direction of the x-axis. And in fourth quadrant, that should be our original angle. Terminal angle is the angle between the the reference angle is the angle between the terminal side and the nearest direction of the x-axis. What are coterminal angles? Think about a situation like this. You have two angles in the standard position. For example, I have initial side and I have terminal side, and this is my angle. Then think of the angle with the same, because it is a standard position, you have to do the same initial side. But what happens for the terminal side, I complete one full rotation of a circle, come back and complete this much, and I call this is the terminal side. So these two angles, they do have the same initial side and the same terminal sides, but the measurement of these two angles are different. Remember, the first angle is an angle between 0 degrees and 180 degrees, the one in the blue. So if I want to maintain the same color, I will say the angle in the blue is an angle between 0 degree and 180 degrees. Whereas when you have drawn the angle in red, it's no longer an angle between 0 degree and 180 degree. What has happened, you have added 360 degrees. So this angle is between 0 degree and 540 degrees. In fact, we can make it look a little more precise. Instead of saying 0 degree, we can say that, think about if you complete one full rotation, that's 360 degrees here. Then if you do 90 more degrees, this one has become 450 degrees. So this red angle is actually between 450 degrees. I'm so sorry, between 450 degrees and 540 degrees. Similarly, you could have said the angle in blue is the angle between, remember this one is the 90-degree mark, so it's an angle between the 90-degree and the 180 degrees. But these two angles are coterminal angles. So what we will do now, we will talk about our final learning objective in this section and start working on some problems. So remember how we have associated the angular measure with the arc length? Now we are going to think about the one other formula that we know have heard so many times and we know so well is the area of a circle. So let's start there. Area of a circle of radius r units is given by the famous formula pi r square. So what I do now, I think of the full circle and I know how much is the measurement of the planar region in this circle of radius r. I know that if I want to find this much area, it's going to be pi r square. But now if I twist the question a little bit and I say that, well, I'm not interested in all of that area. I'm just interested in a circular slice that is intercepted by a circular measured angle. So this is the angle and this angle is represented by theta, and I just want to know area of this circular segment. How do I find it? So it's pretty similar to the process of relating the radius and the arc length and the circular measure. So what we do now, we say, note that full circular rotation is 2 pi. That stands for the area of pi r square. That means if the angle was 1, then that would stand for the area pi r square. Of course, I divide by 2 pi on both sides. So this, after calculation, becomes r squared over 2 because the pi and pi will cancel each other. But I'm interested in the area that is pretended by the angle of theta. So for theta, then, I should get the area to be theta r squared over 2. And that's my area of a sector obtained by a circular section of circular measure theta formula. So we have talked about a bunch of different formulas to interchange between degree and radian, formula to compute the arc length of a circular section, formula for finding the area of a circular section. We talked about coterminal angle, we talked about reference angle, and we're going to practice some exercise problems. Okay, so the first one is find an angle between 0 and 2 pi that is coterminal with the given angle. So we'll first understand what do I mean by 13 pi over 5 and what do I mean by 2 pi. So what I'm saying essentially, if you think of the standard position, the angle 0 is simply the positive direction of the x-axis being the initial and the terminal side for the angle. So that's the angle 0, whereas the angle 360 degree, the initial side of the angle is still the positive direction of the x-axis, but the terminal side has a complete rotation and it's still incident with the positive direction of x-axis, but it has completed a complete rotation for a circle. So these are 0 degrees and 360 degrees, or 0 and 2 pi. So when I'm talking about 0 and 2 pi, initially it would make a little better sense for us if we always think of these things in terms of degree. So even though I said that find the angle between 0 and 2 pi, in your mind you are thinking I'm supposed to find an angle between 0 degree and 360 degree that is coterminal with the given angle of 13 pi over 5. So what I do first, because I'm changing it in the context of degrees, let's see 13 pi over 5 will be what in terms of degrees. Remember the process of conversion. In order to convert a radian measure to the degree measure, you're supposed to multiply the radian measure by a factor of 180 degree over pi. So we'll do that. So we'll say is 13 pi over 5 times 180 degrees over pi. Do the necessary simplification. So pi and pi will cancel each other. 5 divides 180 and gives me 36. So I will cancel these two. That will make me 36 degrees. And then I will multiply 36 degrees with 13. So 13 times 36. And that should be 468. So this is 468 degrees. So what I do now, remember the angle that we're trying to find out is between 0 degree and 360 degrees. So 468 degrees is a little too much. So think about drawing the angle 468 degree. You start here. This is 360 degree. I want 468. So I want 160 more of it. So at this point, I will do 90 more and 78 more, and that should be the angle with the terminal side like this, which is going to be the angle of 468 degrees. So what will be the coterminal angle to this angle, but between 0 degree and 0 degree and 360 degrees? Well, think about it. This is 0 degree, has the same initial side as our angle in blue. If I make this one the terminal side and just do this much of the rotation, so if this is the rotation, then this angle is coterminal with our original angle. But how much is the measure of this angle? Isn't that only 168 degrees? So finally, once I have figured out that the required angle is 168 degrees, I have to remind myself that I'm going to draw this angle and change the measure to the radian measure. So now you have 168 degrees, you change it to the radian measure. And how do you do it? Well, the formula says that to change a degree measure to radian measure, you're going to multiply by the factor of pi over 180. So let's go ahead and do that. So I say 168 times pi over 180. And then we're going to simplify this thing. So remember, I can divide 168 by 36. And how much I get? Well, let's check it. 168 and divided by 36. And so it seems like I cannot divide it. So let's see. I have 100. Oh, I'm so sorry. I made a small calculation mistake here. So see, this one should not be 168 degrees because 468 minus 360 should be 108 degrees. I don't know what I was writing it. So let's just change it real quick. So this one is just 180 degrees. I don't have to change anything else. It's just this much of the calculation and everything else should be fine. So 108 degrees, and I have to change that to 108 degrees as well. So as I was saying, we are going to now simplify this quantity. So to simplify this quantity, we'll divide 108 by 36 and I will get 3. Dividing 180 by 36, I get 5. So my answer is 3 pi over 5. So what is the angle that is between 0 and 2 pi but has coterminal sides with 13 pi over 5? It is 3 pi over 5. So we'll do similar things now. This time we're trying to find out the coterminal angle of negative 17 pi over 3. Now these are a little easier. So before I start working on this thing, let's talk about something a little different. So think about the Cartesian coordinates axis. What is the angular measure of pi over 6 radian? So I want to change pi over 6 because this is a very special angle for us to the degree measure. So think about what I do. I multiply the radian measure by 180 degree over pi. So pi cancels, 6 divides 180 degree, so it becomes 30 degree. So pi over 6 corresponds to 30 degrees. So that's our new relationship. And this is something worth to remember. Similarly, if you want to know what is pi over 3, then what you do, you change it to degree measure by the same conversion formula, and now I get 60 degrees. So what I say, pi over 3 is 60 degrees. Again, worth remembering, because these are things that we will use over and over in our quest of learning trigonometry. One other special angle, and that's pi over 2. So pi over 2, when you change it to the radian measure to the degree measure, what you get is pi over 2 times 180 over pi. So I get 90 degrees. So pi over 2 now and so on will be associated with 90 degrees. Then I will start a process which I call the counting of angle. And the question is very simple. How many pi over 6s are there in one quadrant? What do I mean by that? Remember, pi over 6 associates with 30 degree. So that's 30 degree, 60 degree. So 1, 2, and 3. So in each quadrant, you have 3 pi over 6. So I say it here, 3 pi over 6s. Actually, let me write it in a little different way so that I don't confuse you. So I said 3 pi over 6s in each quadrant. This makes our process of counting so much easier. For pi over 2 now, that's 90 degree. So there is only 1 pi over 2 in each quadrant. It also makes the counting process so much easier. When I'm counting pi over 3, this doesn't quite work in the previous two ways. So what we do, always change pi over 3 to pi over 6. How do you do that? Well, you multiply 2 on top and bottom, and it becomes 2 pi over 6. That makes the process of counting so much easier, because you know there are 3 pi over 6 in each quadrant. So as many pi over 6 we have to count, we will count it, and hence we will answer our question for pi over 3s. So after this small talk, let's go back to our problem, because this is in pi over 3, and I want to understand what will be the coterminal angle. So let's see that. First and foremost, this is a negative angle. So instead of going in the counterclockwise direction, we have to go in the clockwise direction from the standard position of the standard initial side. All right. So what I do now, I first change the 17 pi over 3 to pi over 6. How do I do that? I multiply 2 on top and bottom. That makes this 34 pi over 6. Now pay attention when I count. Remember, there are 3 pi over 6s in each quadrant. So this is 3, this is 6, this is 9, this is 12. This one is 15, this one is 18, this one is 21, this one is 24. I'm still not done. So now what? We're going to start counting from 24 to 27, 30, 33, and remember I need one more, so here. So that is the actual angle in the positive direction. So this angle is 34 pi over 6. But now recall, I had to do this angle in the negative direction. So we'll do the same process, but instead of going counterclockwise, we will now go in the clockwise direction. So let's start working on that. Again, the counting is pretty similar. You count 3 pi over 6s in each quadrant. So this is the initial side. And now I start counting. So this is 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, one more. So that should be the terminal side. And this stands for negative 17 pi over 3. So this one is, actually I can write it as minus 34 pi over 6 because I counted 34 of them, which is negative 17 pi over 3. But remember, your problem is to find the coterminal angle with this one that lies between 0 and 2 pi. So clearly one thing you can immediately do at this point, you can go ahead and say, what if I take this much in the positive? Because your angle is between 0 and 2 pi, it should be positive, so you have to be in the counterclockwise direction, and that will be the coterminal angle. The question will be, what will be the measure of this angle? Well, to answer it, it should not be very hard. Why? Think about, this one was only one count. I had 33 here, this is 34, so this is only one count of pi over 6. So how many pi over 6 I have in this? That will be 2 pi over 6, which is what? Pi over 3. Hence, the coterminal angle is going to be pi over 3. All right, so let's start with our next problem. This problem is actually in the positive direction, and it is 77 pi over 2. So this is a very nice problem. It's going to teach us something very fun. So think about, what about pi over 2? How many pi over 2s are there in one quadrant? Only one, right? So one count will take you to the positive direction of x-axis. 2 count will take you to the negative direction of x-axis. 3 count will take you to the negative direction of y-axis, and the 4th count will bring you back to the positive direction of the x-axis. So this is how we are going to count. So the 1s, the 5s, so this is the next one, 5, the next one is 6, then the next one is going to be 7, and the next one is 8. So we see a pattern. So what are the numbers that will end up being on the positive direction of the y-axis? So it's 1, 5. See, the next one is going to be 9. So it's in a progression of 4. So 9, 13, 17, so on, so on. Whereas on the negative direction of x-axis, you should get 2, 6, progression of 4, 10, 11, so on, so on. And this is 3, 7, progression of 4, 11, 15, 19. These are the things. And it doesn't end, it goes forever. And this one is 4, 8, 12, those type of things. What it tells us, once we have realized this pattern, that if we want to know where 77 is going to stand on which of these axes, the positive x, the negative x, the positive y, or the negative y, what we need to do, we divide 77 by 4 and think about the remainder. So 77, I'm going to divide it by 4. 4 goes only once in 7. 3 and 7 makes it 37, and it goes 9 times in 37, so it gives you 36. So the remainder is 1. Now look for the remainder 1 and on which coordinate axis you find 1. See, the 1 is here on the positive direction of the y-axis. That means 77 eventually is also going to be on the same axis. So what is 77 pi over 2? You do bunch of these rotation. In fact, you do 19 of them. And then you end up here in the positive direction. Because we don't have time to draw all of that, we came up with this manipulative way. And now I know this angle is 77 pi over 2. But I am interested in a positive angle between 0 and 2 pi that is coterminal with this angle. And how do I find it? Well, think about the simple angle pi over 2 with this one and this one as the initial and terminal side. Because the angle has to be positive, that should be my measurement. So the coterminal angle to 77 pi over 2 is simply pi over 2. That will answer my question. Again, 17 pi over 9 is not like the nicer angles, pi over 2, pi over 6, or pi over 3. But we are going to answer the question pretty similar to the first question that I have answered. So let's start there. So what I do for 17 pi over 9, I tend to change this thing to the degree measure, just to understand where should the terminal side be. So 17 pi over 9, in order to change it to the degree measure, I'm going to multiply it by 180 degree over pi. Clearly, pi and pi will cancel each other. 9 cancels 180, gives you 20 degrees. So multiply 17 with 20, it is 340 degrees. So 17 pi over 9 is 340 degrees. So in standard position, if I draw this at positive angle, I start with the positive direction of the x-axis as the initial side. Remember, the limit is 360 degree, but I do not even have to go there. So that is your angle in the positive direction. This is the terminal side, giving you the angle of 340 degrees. So what is the coterminal angle? Well, it is itself, because the angle is already between 0 and 2 pi, or 0 and 360 degree. Answer is itself. So I say 17 pi over 9. Answers our question. For each of these angles below, determine the quadrant in which the terminal side of the angle is found and find the corresponding reference angle. And I'm denoting it by theta bar. So let's try to work on these problems. So again, pi over 3 is a special angle, so I will be using my counting technique that we have talked about. First, change 8 pi over 3 to pi over 6, easier to count. So multiply 2 on top and bottom, you get 16 pi over 6. Then start counting. So this is 3, 6, 9, 12, 15, one more should give you 16. So if I consider this as the terminal side and this as the positive direction and this as the initial side, this angle is 16 pi over 6. So which quadrant is the terminal side? Clearly the second quadrant, so I answered it that way. What is the reference angle? Remember, the reference angle is the angle between the terminal side, which is this one here, and the nearest direction of the x-axis, so that must be this one. And this angle is acute, means it's between 0 and 90 degrees, so always positive. So this is the reference angle. Now, how much is the measure? Well, if you remember, how many pi over 6s was this much? This was only 1 pi over 6, 15 to 16. So how many pi over 6 is the reference angle? Well, there are 3 pi over 6s, so that must be 2 of them. So the reference angle is 2 pi over 6. I can simplify that as pi over 3 answers my question. So it is pi over 3. 11 pi over 4. So this is also a very special angle that probably we did not talk about yet. The question first, you should ask yourself, how many pi over 4s are there in each quadrant? And you remember, to answer those questions, I was changing the special angles to degrees in order to better understand them first. So what is pi over 4? Changing it to degree gives you pi over 4 times 180 degree over pi. So pi cancels. 4 divides 180 degree and gives you 45. So pi over 4 radian measure is in degree measure 45 degrees. So that instantly tells me in each quadrant I have 2 pi over 4. So this is 45 degree, 1 and 2. So let's write it down. There are 2 pi, and these are just for simple calculations. There are 2 pi over 4s in each quadrant. That will help us count this angle 11 pi over 4. So let's start working on that. I want to draw the positive angle 11 pi over 4 first. So remember, 2 pi over 4s, 4, 6, 8, 10, one more. So that should be the terminal side of the angle 11 pi over 4. It is a positive angle 11 pi over 4. And this is clearly the initial side. So the first question, which quadrant the terminal side is still second quadrant. Reference angle, well, angle between the terminal side, which is clearly this one, and the nearest x-axis, and I have to have a positive angle because the reference angle is acute. So how much is that? There are 2 pi over 4s in one quadrant. If this is 1, then that must be 1 as well. So it is pi over 4. So remember this process of finding reference angle, because as I said, this is going to be a major concept for us when we'll be evaluating trigonometric ratios for arbitrary given angles. Okay. So the next one is 7 pi over 6. It should be the easier one because we know the count again. So let's do counting for 7 pi over 6. There are only 3 in each quadrant. So 3, 6. I need one more. So terminal side, this angle in the positive sense is 7 pi over 6 with this as the initial side. So the terminal side of the angle is in the third quadrant. That is the first answer. The second answer is the reference angle, which is the angle between the terminal side and the nearest direction of the x-axis. So this much is the reference angle. Now how much is that? Remember, this is only one count of pi over 6. So the reference angle is pi over 6. Okay. The final one in this category is 3. So since I do not see any degree, at once I will understand this is in radian. Now to answer this question, it will be probably for beginners, it will be easier to change it to a radian, from radian to degree measure to find the quadrant, the location of the angle, and the radian measure. So let's do that. 3 radian, if I change it to degrees, it is 3 times 180 degrees over pi. So this will be easier to calculate in our calculator. Let's go there. So I will do 3 times 180. Let's see, 180, and then I will divide it by pi. Should be here. So the value is 171.887, something around that. So if I draw that angle, it's 171, so it's less than 180 degrees. So that should be the initial side, and the terminal side should be this one. The positive angle is, so let's see the value, 171.8873. Remember, we're still in degrees. So what I do now, I say that the terminal side is in quadrant 2. To find the reference angle, we are looking for the terminal side of the angle, which is this one, and the nearest direction of the x-axis. So this is the angle. How do I know how much is this angle? Well, clearly it's going to be 180 minus 171.8873 degrees. So let's do that in calculator as well. 180 minus 171.8873, which is 8.1127. I want to remind you again, this is in degrees. Your answer should be in radian because the question was in radian. So now we change 8.1127 degrees to radian, and the process is you multiply the degree measure by pi over 180. So let's do that. All we need to do is divide 8.1127 by 180, and then we can go ahead and multiply pi with this thing, and my answer rounded to 4 decimal places is 0.1416, and that is the required reference angle. And that should answer my question. Okay. Our third type of question is simple conversion. So the first one is saying that convert 6 pi over 19 to the degrees. And generally, if I do not tell you how many decimal places, you have to round your answer to always round to 4 decimal places. So this question should be very simple. 6 pi over 19 changing to degrees will be 180 degree over pi. Clearly pi and pi will cancel and we will do the rest of the work in calculator. So we do 6 times 180 and divide it by 19, and that becomes 56.8421 degrees. So that's your answer. It goes in this box. We're going to change the degrees to radians. So remember, this is the negative one. So minus 711 degree, changing it to radians should multiply by pi over 180. So let's go ahead and do it and round it to 4 decimal places. So 711, and this is a negative degree. We multiply it by pi and we divide that by 180. Rounding to 4 decimal places, we get negative 12.4093. So since radian, we're not going to use any unit. So 4093 radians. Okay. The fourth is an application problem. This says that in a circle of radius 4, the length of the arc that subtends a central angle of 308 degree is. So let's think about the situation. A circle of radius 4 units. So this is 4. 308 degrees. Remember, this is 90, this is 180, this is 270, so 308 degree will be somewhere here. So what I'm being told now, I want to find out the arc length that is subtended by this angle of 308 degrees. So what do I mean? From here to here, how much is the length? Let's call it S. So you remember the formula, it is S equal to R times theta. Only note theta is in radians. So the only difficult part in this problem is to remember, if the problem is given in degrees, change it to radian first and then use the simple formula. Okay, so 308 degrees is going to be 308 degrees times pi over 180 radians. And let's use calculator again. So we do very nice. So 308, I divided it by 180 and multiply by pi. So yeah, so it should be 5.3756. 5.3756 radians. So in this formula, S is going to be, remember your radius was 4 units, 4 times 5.3756. So when I multiply these two numbers, what I get? 5.3756 times 4. So approximately 21.5024. 21.5024. And because no specific units are given for the length, I'm just going to say units. Answers your question? The next question is telling you, in a circle of radius 3 mile, the length of the arc subtends a central angle of 6 radians. So this is actually a little easier. And because the angle is in radians, the radius is 3 miles. So the arc length should be S equal to radius times, the radius is 3 times, the angular measure is 6 radians, so 3 times 6, which is 18. And this time the unit is given, so the arc is 18 miles. Now, if you want to remember what is 6 radian, where would we find 6 radian? So you can do two things. You can change the radians to degree in order to just understand what it would look like as in picture. So radians will be 6 times 180 degrees over pi. So we can calculate that real quick. So 6 times 180 divided by pi. So it's around 343 degrees. So basically terminal side should be on fourth quadrant. So it should be something like this. And that should be the angle. So the arc length that we found out is from this point to this point. That's what we found out. Okay, so the next question is area of the segment cut by this arc. So now you want to know, if I'm interested in finding this area, what would that be? Well, we have the formula, remember? It's going to be theta times r squared over 2. So let me go back and show you the formula for arc length and the corresponding angle of angular measure and the area. It's theta times r squared over 2. So we're going to use that formula and answer this question real quick. So now we say for the area, let's call it A. That will be theta is 6 radians again times r squared, which is 3 squared over 2. So that is going to be, you can cancel this 2 with this 6 and get a 3. So it's 3 times 3 squared is 9, which is 27. Remember, this is the area, so we will say squared miles. That will be the unit of the area. And that will answer my question. Okay, my sixth problem is saying find the distance along an arc on the surface of the earth that subtends a central angle of 7 minutes, which is 1/60th of a degree. So degree measure is given. And the radius of the earth is 3,960 miles. So it's a very small angle, but you know the radius is huge for earth. So even the angle is small, the arc length will be substantially big. So say this one is a very small angle. This is 1/60 degrees. We want to know how much is the distance on the surface of the earth between these two places that subtends the angle of 1/60 degrees. So how much is this distance? So this is actually a very nice problem. You're finding the distance between two spots on earth using trigonometry. So what I do first, I change 1/60 to degrees to radian. So that will be 1/60 times pi. It's 60 times pi over 180. Remember, we're rounding to 4 decimal places. So let's do that. We have pi on the top. That's the only thing. And we divide by 60 and 180. So this one is 0.303 when rounded to 4 decimal places. 0.12303. I'm going to use this, and the formula is equal to r theta. So S is what I'm trying to find out. R is 3,960 miles times 0.0003. So let's see that. So 0.0003 03 times 3,960 miles. 3,960 miles. So that should be 1.188 miles. So almost 1 mile. So 1.188 miles. So the two spots on the surface of the earth, that is an angular distance of 1 minute or 1/60 degrees, is at a physical distance of 1.188 miles. Finally, we have the question about Earth one more time, and it says that find the distance that the Earth travels in 1 day in its path around the Sun. Assume that a year has 365 days and that the path of the Earth around the Sun is a circle of radius 93 million miles. So this is the path of Earth around the Sun, say. So you have Earth here. So this is my Earth. And Sun is here. So the radius is given by 93 million miles. What I want to know, how much distance Earth covers in one day. Remember, Earth covers the entire perimeter. So starting from this point, it completes a full rotation and come back to the original position in a year, which is 365 days. So how much is the perimeter? Remember, the perimeter is 2 times pi times r. R is 93 million. So for million, you need 6 zeros. 1, 2, 3, 4, 5, 6. So that's the perimeter. That many miles. But that is covered in 365 days. So in one day, Earth travels 2 pi times 93, 1, 2, 3, 4, 5, 6 over 365 miles. And that should be my answer. I will just find this value, round to 4 decimal places. So let's see. 93, 1, 2, 3, 4, 5, 6 zeros times 2 times pi. And remember, we are dividing by 365. So it's 16009211879. So approximately 1600. So sorry, 921. 921.1879. 1879 miles. So approximately, wow, travels more than 1,000,000 miles a day. Okay, so that answers our question. And this is the end of this section as well. So I hope things made sense to you. Now, once you have done watching the video, you will start working on your homework problems. If you have questions, please do not hesitate to let me know.